Okay, so what I wanted to talk about today is searching for functions. So if I give you certain conditions, do we expect to find functions with certain properties? And the goal for this eventually is to get to lecture 6 for my colleague, where there's a wish list for functions. And if we can find a function that has this property, then we can feed it in, and it's going to give us some great bounds on sphere packing. And if the bound is sufficiently good, it's actually going to give us optimal sphere packings. This is similar to some of the stuff that the L function people are doing, where if you want to try to estimate the order vanishing at the central point or the order of excess vanishing at the central point, we have the number theory, random matrix theory correspondence, we have the n-level density, and if we take a suitable test function, a function that has, say, even, non-negative, then we can get a lower bound. So we can get an upper bound for what's going on at the central point by just throwing away the contribution from all the zeros, other than the zeros at the central point. And it then comes down to what is the best, what is the optimal test function you can take that satisfy all these conditions. And so this is a common theme in mathematics, searching for a representative of a space with certain desirable properties. And so I thought we would just start off by just talking a little bit in general about questions like this, and then just trying to get a sense of what things are. So here's a question. I have a function f such that for all continuous g, we have the integral from minus infinity to infinity of g of x, f of x dx equals 0. What can you say about f? So any thoughts?
Probably yeah.
So we at least know an example.
Yeah.
So we could have f is identically 0. So at least the set of functions, could anything work other than the function that's identically 0?
0 almost everywhere.
Good. So we could have f is congruent to 0 almost everywhere. So because of crap like this, it means we might want to change what we're searching for. Rather than searching for a function f, what kind of function might we want to look for? So I don't have to worry about this almost everywhere. What condition should I add to my function? Continuous. So make f continuous. So now if you make f continuous, that would eliminate the f is congruent, the f is 0 almost everywhere. So what do you think is true? If now we assume that f is continuous, do you think the only thing that works is the 0 function?
Yeah.
All right, any thoughts as to how you would prove that?
I think you can pick a function g that just like steals the support of f, just like scoops it up.
Good. So what does it mean? So assume there exists an f which is not identically 0. That means there exists an x naught such that f of x naught is greater than 0 without loss of generality, because why would we choose the x naught to be negative? Just multiply by -1 if you need to. And so that means there exists a delta such that if x minus delta, if x minus x naught is less than delta, then f of x will be greater than 1/2 f of x naught. And so here's the point x naught. Here's a little delta band about it. And we know here's f of x naught. Now here's our epsilon band. And so we know the function has to be at least a certain amount, at least 1/2 f of x naught in this region. So now what do we do for g? Yeah, so we just want some kind of continuous function g. And so one possibility is to take, a triangle function, and if you want to be safe, you can have it come in at, maybe half delta on each side. Doesn't really matter. And this is enough so that, you have some region in here where everything is going to be positive. So this shows that if you have a condition like this, the only possibility would be for f to be identically 0. Okay. What this shows is that we actually have a need to be able to construct continuous functions with certain properties. So a key part of this was I wanted a continuous function that was positive at a point, and in fact positive in a region. So we needed a continuous g that was positive in a region. So this is just one condition because I made it very concise. So can you always do something like this? Well, at least if we're in Euclidean spaces, if we're in R squared, R cubed, got to the end, that's not going to be a problem. And so depending on your preference, yeah, of course, my spaces are always going to be R to the n, C to the n, or something like this. This is not a big deal. When I was in college, I was always upset when theorems were not proven in the greatest generality. Now that I actually use theorems to prove interesting things in number theory, oh yeah, my function of course is Schwartz. How could my function not be infinitely differentiable, hopefully? So you have to decide how much do you want to push this to. Do you want to consider an arbitrary metric space, a topology? How far do you want to try to push something like this? And then try to remember, okay, does this book use, in part of the definition of the space is also Hausdorff or not? So we're going to do a search for functions that have nice properties. And so here's the question. A and B disjoint in R. I want a continuous f such that f of A equals 1, f of B equals 0. And hopefully the notation is clear. I could write maybe the image of A is 1 and the image of B is 0. So basically, in some sense, I want to separate two sets A and B. So the first question is this sometimes possible? And then the next question, is it always possible? So can you give me a pair of A and B where you can do this?
But like if A is R and B is the empty set.
Okay, so one possibility is A is R and B is the empty set. So the way we have things defined, does this work?
Oh, or disjoint is like a thing.
Well, disjoint means they don't have an element in common. R and the empty set don't have an element in common. What this means is, if you take any element in B, f of that is 0. There are no elements in B. So the way it's phrased, you are, I believe, correct. My book freshman year says at one point, sometimes considering the empty set as a vector space causes pathological counterexamples to theorems that we want to be true. So henceforth, we will always assume that our vector space is not the empty set whenever it causes trouble. But absolutely fine to start like this, and that's a really good thing to talk about. So can you give me a non-trivial example?
2 points.
2 points. So A equals 1, and there's 2 possibilities for B.
0.
0 is one of the possibilities. And what's the other possibility? Yeah, -1. I would say that those are really the only possibilities. Is you take the points 0, 1, or you take the symmetric 1, -1. And again, part of this is just trying to think of good ways to come up with examples. All right, so what would be your function? So if we do this case, I want a function that's 1 on A, 0 on B.
Y equals X.
Yeah, this is just screaming f of x equals x. more generally, it's not that hard to do.
Yeah.
And it's not that hard to keep it continuous. So let's make the problem a little bit harder before we go on. Or you want to give me just one more example? Because so far these examples are a little bit trivial.
I think like if you have any two sets that are like separated by a gap.
Okay, good.
Yeah.
So let's take a gap here, x. And let's take maybe the integral 1 infinity for 1. And negative 1 infinity, negative infinity for the other. And now we have a sizable gap between them. So now how would you define it?
A smooth indicator of the non-negative reals.
Okay, so can you?
0, 0, 0. Whoop. 1.
So f of x equals 1 if x is greater than or equal to 1, 0 if x is less than or equal to negative 1. And we want to go from negative 1 to 1. So x plus 1 over 2, I think, for negative 1 plus over to x plus equal to 1. So that's a nice example that would work. And we've done it explicitly. We can, of course, also use one of my favorite functions of all time. I think this works. So when you take x equals negative 1, you get 0. When you take x equals 1, you get 1. So does anybody remember my favorite or least favorite function from real analysis? This is the function that shows you why real analysis is hell and why complex analysis is a joy, because this function is not allowed into complex analysis. It's not complex differentiable.
Oh, e to the negative 1 over x, right?
Yeah, e to the negative 1 over x squared if x is not 0, and 0 if x equals 0. Every derivative of this function at 0 is 0. So if you look at the Taylor series of this function, it's identically 0. If you look at your plot, as x goes to infinity, what does this function go to?
1.
1. So the function is going to look something like this. Right? So there's a lot of nice things you can do with this. You could, for instance, look at 1 minus f of x, which would start at 1 and then rapidly and so I have set up a Mathematica Notebook, and then rather than putting it on the screen, this is a slight modification. So this is the function f of x is if x is greater than a and less than b, it's e to the negative 1 over x minus a, b minus x. And so I've got some little window over here where the function is clearly going to be positive, and then it's defined to be 0 if I'm less than a or greater than b. And it's set up so that I can zoom in a little bit, so I can change where my left and right endpoints are. Oh, wait a minute. What I want to be doing is I want to share the screen. Okay. And so, I can move the left endpoint, I can move the right endpoint, and as I move these, very close to each other, you can see over here, it's moving, but still decent size. Now let's move the right endpoint. It's much, much closer. And you can just see that, for all practical purposes, Mathematica is saying, I refuse to draw this. It's just so sharp as you get near A or B. But what's great about this is I can ask questions about differentiability. If I give you this function f of x, I can ask, how differentiable is this function at the point I care about? And so right now we were just going for your continuous f. What if I want a continuous and differentiable function? How much worse is it to add something like that? And now I have The next condition I might want is, maybe I want, add the condition that 0 f of x is equal to 1. I want something between 0 and 1. I want to be 0 if I'm in B, 1 if I'm in A. And so in this case, that's not a problem. Your function actually satisfies that. This is a really nice function to be aware of. This is a generalization, e to the negative 1 over a minus, no, x minus a, b minus x. That's a great function to look at, or 1 minus that. All right, so here we have something very nice, and we have a gap. And so what might be the case is that if your sets have some additional structure, the problem is a lot easier. And so first try to solve in the special case where you have some additional structure. Try to figure out what structures are nice, and then hope that maybe in what you're trying to study, you might actually have that at your disposal. One of my favorite problems in all of mathematics involves a question about e and pi. Have I shared this with you about the transcendence of e plus pi and e times pi?
Oh, yeah.
So we know either e plus pi or e times pi is transcendental. We believe both. And you think that maybe e to the I pi equals -1 has a role to play. No, it's basically the fact that algebraic plus algebraic is algebraic, algebraic times algebraic is algebraic. And so if e plus pi and e times pi were both algebraic, then e plus pi squared minus 4e pi is e minus pi squared is algebraic. And then you would get to the square root of that, or e minus pi is algebraic. And then you would get e plus pi, e minus pi. Okay, but when you add them, you get e and pi algebraic. So there's really nothing special about e and pi going on here, but you could be misled. And so that's a really good warning to have as you're doing any calculation like this. If I'm looking at a special case, maybe there is a proof that uses the fact that e to the I pi is -1, but that's not going to be a proof that generalizes. So we can come up with maybe a proof using Rapness. So consider AB with a gap G. So that means for all AB, the distance from A to B is greater than or equal to G. Can I find a function f from R to 0, 1 continuous such that f of A equals 1 and f of B equals 0? Any thoughts?
You could set f of A to be 1, f of B to be 0, and then linearly interpolate.
All right, so f of x is defined to be 1 if x is in A. F of x is defined to be 0 if x is in B.
Are we all assuming that the sets are like connected? Because they're not.
So what sets A and B are we talking about? Because we want this function to be continuous.
Well, if there's a gap, then when you linearly interpolate, and if you have if you have like A to be like a Cantor set, and then B to be a Cantor set 5 units to the right, if you linearly interpolate the A's, you'll just get a line, and the B is over here. As long as there's a gap, you should be able to.
So one thing is, so what is your function? So you told me that I'm setting it to be 1 for everything in A, I can do that. I'm setting it to be 0 for everything in B, I can do that. You now have the rest of the real line to define that. So tell me the value anywhere else.
Okay, if it's between 2 points of A, it's 1. And there's
So if
no,
it's
with no
between 2 points of A,
with no point of B.
well, what if this is part of A here, this is part of A here.
Well, yeah, with no points of B in between. then it's one.
But I could have infinitely many. Now, of course,
No,
there's
yeah.
a gap.
So you just, I mean, really what you do is you look at the point before it, A union B, and the point after it, that's in B, and A union B.
Okay, so take X in R minus A union B. Okay.
Look at the points ahead of it, or look at the first point behind it. That's in A, or the accumulation point of one of those.
Okay, so look, so right now A and B are not closed.
Sure.
So do we want to consider A and B closed?
I mean, if there's a gap, you can just close both.
So let's consider closed sets. But again, this is what I want, is I want a discussion like this to decide what kind of properties do we want to assume about our sets A and B. Is it a big deal to close A and B if they have a gap? No. Yeah, we're just adding the limit points. So that doesn't seem like that's a big deal. Okay, so now we have closed sets A and B. So now if you want to talk about the point to the left that's in A or B, we should be able to do that.
Yeah.
Okay, so look at S left, which is in A or B. First point in A union B to the left. Okay, so in fact, let's call that X sub L. And similarly, we'll have X sub R. So we have four possibilities. It could be AA, AB, BA, or BB. Okay.
And then connect them with connect like the X comma Y coordinate with a line in it.
So if it's AA, what can we do?
Have it be one.
Yeah, have it be 1. And if it's BB, 0. So now we only have the AB and the BA, by symmetry they're the same. And so now how would you define it? So let's assume we're in the AB case. So we'll have the maybe X sub A plus equal to X less than equal to X sub B.
Wait, what are X sub A and X sub B?
Well, this is the X sub L,
Oh, okay, I see.
and this is the X sub R. But since we now know that it's an A and B, let's just call it like that. So we have, something like this. Here's XA, and this is where A lives. Here's XB, and here's some point X. And we want it to be 1, we know it's 1 here, and we know it's 0 there.
Well, if it's 0 to 1, then you could just do X minus XA quantity over XB minus XA.
I think you have it backwards.
And then I think you take 1 away.
I think you want X minus XB over X minus XA.
Oh yeah, I just flipped it so 0's on the left because that was the easiest way to think about it first. Oh.
So if I do it like this, when X equals XA, I get 1. When X equals XB, I get 0. I think that works.
And it's a line.
And it's a line. So that would be a function. And so that would linearly interpolate it. So this works if we have a gap. Is there any other way to look at these gap functions? Hello. So if I look at the distance to A,
That's cool.
right? What's that distance going to be? It's going to be 0 if x is in A, 1 if x is in B. And I also have the distance from x to B. Those might be really good ingredients to use to build a function. So what function would you want to build now? So I want something that's going to be 1 if I'm in A, 0 if I'm in B, and it's going to be between 0 and 1. Any thoughts?
Distance x and a, you just look at distance x and
Mm-hmm.
a. If it is less than g over 2, then you just go all the way up above to 1. So it goes up, it starts at 0 at g over 2 and then it gets to 1. Right? G
Right, but so
at
you
0.
give me a long convoluted.
Okay, sure.
Right. Let's look. So no, but again, this is the whole point of the discussion. Is I want to talk about high-level ways to look at this. What do you notice about this? We have a really nice structure.
Yeah.
We have one place where our x is occurring. We have a couple of other things, but x of a's and x of b's are very nice. Maybe some kind of ratio combinations of these could be useful. What if I tried something in the form, alpha distance x a plus beta distance x b over gamma distance xa plus delta distance xb. Could this be something worth studying? Sure. I mean, it kind of feels a little bit like that. Are there good choices of alpha, beta, gamma, delta? And we want this to equal 1 if x is in A, 0 if x is in B, and 0, 1 always.
The first condition forces beta and delta to do the thing. I don't like that.
So why did the first? So if x is in A, then these are both 0. And so good. So if we want this condition to be true, if 1 for x to A, these no longer matter. And so beta has to equal delta. So this forces beta equals delta. So there's two possibilities. Beta equals delta equals 0. Beta equals delta does not equal 0.
Alpha.
So do we agree that either beta equals delta equals 0 or beta equals delta does not equal 0? If beta equals delta equals not 0, what can I assume about beta and delta?
1.
Yeah. So in this case, without loss of generality, beta equals delta equals 1.
I don't like it being 0.
Yeah, I mean, to me, if it's 0, now all of a sudden we just come down to here, we have the distance from x to A and the distance from x to A, that's just going to cancel. But also, of course, when x is in A, that's 0, we'll have 0 over 0. So this scares me. Right? So, again, we're now at the point where we can, without loss of generality, we can assume that those are 1, and we can always adjust alpha and gamma accordingly.
And then.
And so now, if we're in A, these cancel and we get 1. What if we're in B? If we're in B, these are going to be 0. What do we need to be true about alpha and gamma? Alpha needs to be 0. So this now forces alpha equals 0. So really, it's going to simplify to the distance from x to b. And what do you want to choose for gamma?
simplest thing if the definition line, choose one.
Yeah, just one. You know, distance XA plus distance XB. I think any gamma greater than 0 would work.
Wait, but, so if X is in A, then like,
If X is in A,
oh, sure. Wait, but the distance, oh, sure, so that's 1. Oh, yeah,
Yes.
okay.
yes. So I think any gamma greater than 0, I think works. So the simplest one is gamma equals 1. That's a really nice, simple formula. You know, we're not writing down interpolations, we're not, you know, setting conditions, well, if this end, we're going to walk like this. Does this work for the original problem?
We would need to check if it's continuous.
So that's the main question is this continuous?
Null requires always greater than 0, and these functions are continuous.
So if there's a gap, this works. So if gap, okay. Right? So as long as there's a gap, I think we're going to be fine.
Do you need a gap or do you need the closures to be disjoint?
So if the closures are disjoint, you can get a point that's getting very, very close. But if it's getting very, very close to both of them, then the numerator is also going to 0. So you might be okay. So, you know, that's something to think about. You know, would this work if there's no gap? We will assume that the sets are closed, so we'll assume that the sets are disjoint, because if there's an element in common, you know, there's no way we can do this. So clearly we have to assume that A and B are disjoint, so closure A, closure B are disjoint. But you could have, you know, there's like alternating Cantor sets and Cantor sets going off to infinity, you know, getting closer and closer and closer to each other. Could that cause a problem? I'm sorry?
Awful construction.
Right, and so you know, if you have terrible sets like that, you're in trouble. If you have a lattice packing, I'm not worried about, you know, anything like that with a nice regular lattice pattern. So in terms of how far you want to push something like this, if your space of your A and B are anything nice, this is going to be more than enough.
Wait, it's not Wednesday, that's why it's. I'm just not on my best this week.
I actually just got back from Michigan earlier today.
Are you doing things?
I was doing things, yes, doing entertaining things at breakfast.
Oh, great.
So this definitely works, and then I'll leave it as an exercise to think about how far can you push this, and could we make something like this more differentiable? Yeah. Is this differentiable? If so, how many times?
Let's see. Linear function, numerator.
Yeah, but you've got like flat and then like comes to an angle. So it's that.
Well, if you're walking away from, let's say if you're walking away from B, then numerator is just going down linearly, and the denominator is going up linearly. No, the numerator is going up, and the denominator is going up a little bit faster. But the ratio is constant.
So one way you could write this,
Wait. No, the denominator is constant.
this is the same as 1 over 1 plus distance xa over distance xb. Or you could write it, I could add distance x over a and then subtract. And I could also say this is the same as 1 minus 1 over 1 plus distance xb over distance xa by just adding and subtracting distance xa. So here are two equivalent formulations of the problem we have.
Well, I think I like the first formulation because actually the denominator is constant. if you walk like the denominator, I mean, okay, so if you're in neither set and you're just moving around,
Right.
then the denominator is constant.
If you're, because like you could
Not
move it
necessarily.
away from both.
So
of them.
here's A, here's B, and I'm far to the left.
Right.
And then as I go further, I'm getting further from both A and B.
True.
So we don't know that the distance is constant
True.
in the denominator. So there's a lot of things to think about.
Yeah.
And so the key word I was mentioning earlier was Uryshon's lemma. So I'll let you, Google that later. And it's talking about trying to construct a function that basically splits two sets in various types of spaces, where the function will take on values between 0 and 1. It'll be 1 if you're in one set, 0 in another set.
I think you can do this with smooth functions if you're compact and disjoint or something. Compact and have a gap. If you're compact and have a gap, we proved this in a minute.
Right, and so there's a whole series of things you can try to do to smooth things out. We do have those nice functions we looked at earlier. Could we maybe put that in as an input? Other things that people sometimes do is they do like a dyadic decomposition, and they will have like little rings around your sets. And just in this ring, we are separated by at least this amount. So there's lots of games you can play.
Yeah, can't you do, you could place two.
It's been a while since I've played these games. Nice jump.
Yeah, you get two sets. These are compact sets.
Right.
With different balls around them.
Yep.
This is our guy. This is a ball around him. And then you like do, what do they call them? I call them gluing functions. You do like the exponential, like weird guy
Right.
here, and it's like 1 in this interval.
And it goes down to
0
1/2.
here.
Or
Yeah,
something like that.
yeah, it goes down, and then you can paste.
And then you have the other one starts off at 0 and goes up to 1/2. And then you define it to be constant between, or something like that.
Yeah, and you can paste.
There are games you can do like that. And we do have that function that is infinitely differentiable. If you have these sets that are well separated. The problem is if you have infinitely many interspersions. If you have Cantor set and Cantor set or something like that.
Is that how you get the smooth cutoff function with the e to the negative 1 over x squared? Business with that?
I'm not sure.
That's what I'm using.
I mean, in a situation like that, you could use that and then you can adjust that so it comes down to 1/2. But you've got to be careful that you make sure that you have all the derivatives you want. And so smooth is infinitely many.
Well, if you do whoop, and
Right.
if you hit 0 and then just stay 0 forever,
Exactly.
that's like a smooth drop off.
Yes. And the e to the negative 1 over x squared, that hits 0 at 0.
Right.
And so you can do something like that going from like, and we could adjust it using the e to the 1 over like 1 minus x squared or x squared minus, I think 1 minus x squared. And then that's going to hit 0 at plus minus 1 and give you all the derivatives you need being 0.
Sure.
So something like that might be the way to handle something like that, where now your x might be these distance functions.
It's how you do integration. Build.
So these are games to play. So again, this is not related to the direct material in lecture 6. This is related to the high level of thinking about how would you try to come up with functions like this? What would you do? What properties do you want to add as you're going through? And so we first start off with, let's take the reals and an empty set, the most extreme difference possible. And then it becomes a real question of just trying to analyze, does this actually satisfy the conditions? I remember your freshman year, we finally realized that the solution to one of the problems was by definition. It was just a convoluted way of just unwinding what the definition was of something. Then we tried to come up with a series of examples to build our intuition. Let's start with 2 separated points. For the people who are doing Uryshon distance, what kind of configuration we want to put the points in. The most natural is 0, 1 or 1, -1 to have something balanced. And then how do we generalize that? Well, we then have 2 sets with a gap. And so it's very natural to consider 1 onward, -1 onward. And so, again, there was a really logical progression of how to do stuff like this. And then trying to explicitly do our function and putting in the condition of, being between 0 and 1, or with the -1 to 1, we could just interpolate that linearly. With the -1 onward, we could also do that linearly with the interpolation. For more general sets, it became a little bit harder, but we had a nice construction here where we can say, well, look, walk to the left, walk to the right, because our sets are closed, there will be a unique first point in either A or B that you hit, because there's a gap between them. If there isn't a gap, would there be a problem? The sets are closed. And so I think you should still have a unique first point of A or B. Because, again, just look at, points of A going to the right, that's the next. Because it's a compact set, it has to have a largest value. And same thing for the B, so there has to be one of them that you will hit. So with a bit of work, you can actually justify the existence of a point XA and XB, and then do a construction like this. This, I think, is much faster. And what I like about this is you have some idea of the functional form, and you're just trying to guess how things come together. So I'll end with just one last example of trying to guess the functional form of something and just how valuable it is. You could do it with probability. What is the probability of A union B, and just trying to guess something like that. I will do it with the product rule. So imagine I have far more power than I do, and I decide to give some of that power to you, and I will allow you to redefine differentiation of products. Okay? What would you have the derivative of a product be?
The product of the derivatives.
The product of the derivatives. And your students would worship you and thank you, and they would have sacrifices to your generosity. And of course, what would you then do for the quotient rule? The derivative of a quotient is the quotient of the derivative, right? You're not going to toy with your devout followers, right? You're going to keep them happy. Well, we don't have that. We have, let's say f of x, g of x is some function a of x. And we want to find a prime as a function of f, g, f prime, and g prime. So I'm assuming everybody has seen the proof of the product rule where you add 0 in a clever way and then just do some algebra. Did anybody, you haven't seen this?
I'm assuming I've seen it at some point, but I don't remember.
Okay, so you always start off with the definition of the derivatives. The limit as h goes to 0 of a of x plus h minus a of x over h. So this is going to be the limit as h goes to 0, f of x plus h, g of x plus h, minus f of x, g of x over h. And this is the advantage of working on a blackboard that's very long, is I can leave a gap here deliberately. And so if I subtract f of x, g of x plus h, and add f of x, g of x plus h, amazing, look, just the right enough room. It's almost like I've given this lecture before, right? So now this is the limit as h goes to 0, f of x plus h minus f of x over h times g of x plus h minus f of x, g of x plus h minus g of x over h. And now we do the limit of a difference is the difference of the limit of a product is the product of the limit, so long as the limits exist. And when you apply the limit rules, you'll get f prime of x, g of x, oh, sorry, that should be a plus sign, plus f of x, g prime of x. So that's the standard proof of the derivative rule by just doing the algebra. Okay. But imagine we didn't see adding 0. You know, it's really one of the only things we can do in mathematics. We can add 0 and we can,
Multiply by 1.
Multiply by
and
one.
roll over non-trivial characters that come by 0.
so
Tricks.
give me a function whose derivative you know.
Sine.
No, that's hard.
X.
Okay, x more generally,
1.
Actually,
x to the n. Give me another function whose derivative you know.
X to the m.
X to the m. And then a of x is going to be x to the n plus m. And so now we can form a table. F prime of x is n x to the n minus 1. G prime of x is m x to the n minus 1. A prime of x is n plus m x to the n plus m minus 1. And now when you look at this, how can I get an x to the n plus m minus 1? Yeah, I can multiply these two together or these two together. And so if I look at f of x, I'll do it this way, f prime of x, g of x, plus f of x, g prime of x, it's a prime of x. So I start with two test functions, which I can differentiate, and I can also differentiate the product. And I can use that to get a possibility for the product. It's not a proof, but I now have a feeling that maybe the product rule is f prime g plus fg prime. If I want to do your example, so you said sine of x? So let's assume we know the derivative of sine of x. So sine of x, f prime of x is cosine of x. I need to multiply this by a function such that I will know the derivative of the product.
yeah.
There is a choice.
1 over sine of x, but then how do you,
Yeah. So what can I multiply sine by and have the product being something that I know? And again, this is all about pattern recognition.
Oh, 2 cosine.
Yeah, 2 cosine. So I'm glad that you put in the 2. It's going to make my life a lot easier. Because if you put in 2 cosine, now you get 2 sine x cosine x, which is sine of 2x. So a prime of x is going to be 2 derivative of sine is cosine 2x, which we may need later is cosine squared of x minus sine squared of x. And so g prime of x minus 2 sine of x. So the way I always remember this is the derivative of sine or cosine, one of them has a minus sign. It goes together like that, SIGN. You can also, of course, just draw the circle fully, and when you draw the circle, you can see, okay, as I'm moving like this, sine is getting larger, cosine is getting smaller, so the derivative of cosine should be negative. And now if I look at, I thought it might be f prime g minus plus f g prime. F prime g is going to be 2 cosine squared of x, and then g prime f is going to be minus 2 sine squared x, and factor out the 2. And there you go. Are you more convinced now that this is the product rule? This is a much better example than just x to the n and x to the n. Maybe x to the n, x to the m is too simple of an example. But here now I'm doing trig functions, and I've got a good trig identity. Almost surely this is a lecture I've given before, because I immediately said, well, I want to write 2 cosine 2x like this. If you don't do that, what happens when you reach this point? It doesn't look like it works. And so this is a great argument for why we actually teach you various things. We want you to recognize when you have the same expression written in a different way. The story I heard is that Kepler actually had the equation of Mars traveling in an ellipse, but it was not written as he was used to an ellipse being written. He goes, damn it. If only I had an ellipse, I had this instead. All right, so this is, I think, a good place to start. This was an amazing amount of material in terms of just ways to think about mathematics. In terms of content, it was actually very minimal. But this is really what I want to try to emphasize with the book. I really want to try to emphasize perspectives, ways to look at problems, ways to try to come up with what the answer might be. All right, so I will send an email to all later. I have to run off to